In this video, we'll understand instruction tuning in a simple step-by-step way. We'll see why base language models are not naturally good at following instructions, how instruction tuning fixes that, and why it became such an important part of modern generative AI. Instruction tuning is a fine-tuning method where a large language model is trained on examples of user instructions and good responses. The goal is not just to do one task better, but to make the model generally better at following instructions from users. Instruction tuning is one part of the broader fine-tuning family. A pre-trained foundation model already knows patterns from massive text data, but it still needs adaptation for practical use. Instruction tuning helps bridge that gap between raw language ability and real user expectations. A base LLM is mainly trained to predict the next word in a sequence. That means it does not truly answer a prompt in the human sense, it simply continues the text. So if you ask, "Teach me how to bake bread," a base model might complete the sentence in a grammatical but useless way instead of giving proper instructions. Now let us look at this in a simple table format. Instruction tuning vs multitask fine-tuning. Why explicit instructions matter? A key comparison from the FLAN work asked an important question. Are gains coming from many tasks alone, or from the instructions themselves? The results showed that natural instruction-style inputs performed best. So the wording of instructions is not a small detail. It is central to better zero-shot behavior. Training a large language model from scratch is extremely costly in time, compute, and data. Fine-tuning an already trained model is far more practical. And with parameter-efficient methods like LoRA or partial fine-tuning, the cost becomes much lower while still improving behavior. Now that we've covered core idea check, let's test what we've learned so far. Here's quiz number 1. See if you can get it right. Question 1. What is the main purpose of instruction tuning? The correct answer is to improve instruction following. Instruction tuning helps a model respond better to user requests and follow instructions more reliably. Question 2. Why do base LLMs often give odd responses to prompts? The correct answer is they mainly predict next words. Base autoregressive LLMs are trained to continue text sequences, not naturally to behave like helpful assistants. Question 3. Why is fine-tuning preferred over training from scratch for many use cases? The correct answer is it uses less compute and data. Fine-tuning adapts an existing model and is much more efficient than full pre-training. Instruction tuning is usually done through supervised learning. The model sees labeled pairs, an instruction-like input, and the desired output. During training, the model's weights are adjusted so its responses become closer to those target answers. Each training example usually has 3 parts. First, an instruction, such as translate this sentence to Spanish. Second, optional extra context, like a passage or supporting details. Third, the desired output, which acts as the ground truth the model should learn to produce. One of the biggest benefits of instruction tuning is generalization. When trained on many varied instruction-following tasks, the model often becomes better even on unseen tasks. It also reduces the need for long prompt engineering or many few short examples, because the model has already learned the pattern of following instructions. Now that we've covered method and evidence, let's test what we've learned so far. Here's quiz number 2. See if you can get it right. Question 1. Instruction tuning is typically based on which learning setup? The correct answer is supervised learning. The model is trained on labeled instruction and response pairs. Question 2. Which 3 elements commonly appear in an instruction tuning sample? The correct answer is instruction, optional context, desired output. These parts define the task, provide context if needed, and show the target response. Question 3. In the FLAN comparison, which setup performed best on zero-shot instruction following tasks? The correct answer is FLAN instructions. Natural instruction style inputs gave the strongest results, showing that instructions themselves matter. Instruction tuning does not replace other methods. For example, chat models often use both instruction tuning and RLHF. Instruction tuning teaches the model to follow requests better, while RLHF is often used to improve qualities like helpfulness, honesty, or safety. Another important extension is chain of thought fine-tuning. Here, the model is trained not just to give an answer, but also to produce reasoning steps. Research shows this can improve performance on arithmetic, symbolic, and logical reasoning tasks, especially in zero-shot settings. The main idea is simple but powerful. Pre-training teaches language patterns, but instruction tuning aligns those patterns with what users actually want. That is one big reason modern LLMs feel more assistant-like, useful, and predictable than plain base models. Now that we've covered final recap, let's test what we've learned so far.
Here's quiz number 3. See if you can get it right.
Question 1. What problem does instruction tuning mainly solve? The correct answer is mismatch between next word prediction and user intent. It helps bridge the gap between what the model is trained to do and what users expect it to do. Question 2. How does chain of thought fine-tuning help? The correct answer is by teaching stepwise reasoning. It encourages the model to work through problems more logically instead of jumping straight to an answer. Question 3. Which statement is correct about instruction tuning and RLHF? The correct answer is they are often combined in chat models. Many modern chat models use instruction tuning for instruction following and RLHF for behavioral alignment. That's the essence of instruction tuning. If you want, I can also turn this into a scene-by-scene storyboard, voiceover script, or YouTube-ready lesson format.